Let's have a look at how we can deal with really big numbers in maths. Let's find a neat way of writing really big numbers in a much neater and tidier way. And I've got a few examples here. I'm going to start with a fairly small number just while we have a look at the concept, and then we're going to put it into practice with some bigger numbers over here. So let's have a look at this first one. 8,000. What is 8,000? It's 8, lots of 1,000. It's 8 thousands, isn't it? So we could rewrite 8,000 by splitting it into two factors, two numbers that multiply together to make 8,000. 8 times by 1,000. 8 lots of 1,000. From a previous video, we've already seen that 1,000 is 10 times by 10 times by 10. And if we look at our index notation, using the index or the small power notation, then we know that that is 8 times by 10 to the power of 3. So that's a really neat way of writing 8,000. Probably doesn't save you that much ink actually, but when we start to look at much bigger numbers, we'll see why this concept is really useful. Let's have a look at this one. 2,400,000. Okay, it's a bigger number. We're going to do just the same as we did over here. We're going to say we want two numbers that multiply together to make 2,400,000. And just like we did over here where we took out the 8, here we're going to take out 24, because that's what our number starts with, 24. So what do we have to multiply 24 by to give us 2,400,000? Well, we can multiply it by 10 to give us 240, by 100 to give us 2,400. And on it would go, actually, what we're multiplying 24 by is 100,000. 24 lots of 100,000. That's what we've got there. Just like we did over here, if we rewrite 100,000 in index form, rewrite this as a power of 10, well, it's 10 times 10 times 10 times 10 times 10, or 10 to the power of 5. So again, we've found a neat way to do it, but there is a difference with our first example. And it's an important difference. What we're getting towards here is something called standard form or scientific notation. And it means that we write two numbers. A number times by a power of 10. A number times by a power of 10. But the number must be less than 10 itself. So this is fine, but this is a problem because our number is bigger than 10. So we need to deal with that. 24 times by 10 to the power of 5. Well, 24 is actually 2.4 times by 10. And then if we're to multiply that by 10 to the power of 5, well, we've now found a number here which is less than 10. So we're good. If we look at our powers of 10 over here, well, if we've got 10 to the power of 5, and then we multiply that by another 10, we've got 10 to the power of 6. 10 times 10 times 10 times 10 times 10 times 10. And that, because our initial number is lower than 10, is in scientific notation or standard form. Let's have a look at a quick way of getting there, because this is our longhand approach, if you like. If we have a look at a quick way, 347 million. Again, I'm getting into territory of even bigger numbers now, but we can use this for much larger numbers than this as well. 347 million, okay. Remembering that our initial number has got to be less than 10. So, 347 million, what are we going to start with so that our number just goes under 10? 347, too big. 34.7, too big. 3.47. How about that? 3.47. Less than 10, so we're good. But what are we going to multiply 3.47 by in order to get 347 million? We're going to have to multiply it by 10 a number of times, or 10 to the power of something. But 10 to the power of what? Well, our 3 is currently over here. Way, way, way to the left from where we actually want it to be when we're bringing our 3 right over here to sit alongside the decimal point. But how many places have we brought it over? We've brought it over 1, 2, 3, 4, 5, 6, 7, 8. To put it there, the 3 is next to the decimal point, 3.7 times by 10 to the power of 8. And that's how we express very big numbers in scientific notation or standard form.
Okay, Mary, so let's have a look at this one. So solve x plus 2x equals 12. So what do you think you do first?
Okay, well, I want x on its own, so I would put x equals 12 minus 2x.
Okay, so a lot of the time we want to get x by itself, but what we want to do first is get all of these x's together. So can you see anything we can do with this? Get all these together in one place.
Oh, okay, it's 3x, isn't it?
Yeah,
so
absolutely.
3x equals 12. Oh, and so x equals 4.
Brilliant, spot on, well done.